All right, grade 12 chemistry. Let's learn more about alcohols. We talked about alcohols in the previous video, but now we're going to learn about more reactions with alcohols. Alcohols do a lot of different reactions. Here we're going to specifically talk about their oxidation, the oxidation of the alcohol group, and further oxidations. So we're going to learn about three different functional groups today: aldehydes, ketones, and carboxylic acids. We'll obviously learn how to name them. And then some reactions of aldehydes, ketones, and carboxylic acids. And we'll learn of something called prefix naming, which is what happens when you have multiple functional groups on the same chemical. So, starting with this, just a little review of alcohols. OH is the alcohol functional group. And the exception is carboxylic acids, which is one of the groups that we're going to see today. We've learned a few different functional groups. We've learned these 6 so far, right? Alkane, alkene, alkyne. There's a cis alkene, right? Then there's benzene, or the phenyl ring. And there's alcohol, and we've learned alkyl halide as well. So today we're going to add 3 more to that repertoire. First things first, we're getting into these reactions called oxidation reactions. One thing to keep in mind up here is the oxidation has other definitions in chemistry as well. This is the organic chemistry definition of oxidation, which transforms, say, an alcohol into a carbonyl group. And does some other things as well. But there are other ones, other oxidation reactions that we can talk about as well. In fact, we have a unit about that, Unit 5, Electrochemistry. To do oxidation, there's always, reaction conditions. This is the symbol for oxidation, just an O in square brackets. There's a few different types of oxidizers. An oxidizer, it adds oxygen to a molecule. Popular ones are KMnO4, potassium permanganate, or hydrogen peroxide. Certain acids like sulfuric acid is a good oxidizer, nitric acid as well. So it adds oxygen or strengthens the connection to oxygen. So we're going to strengthen the connection to oxygen here. We're going to make this carbon more connected to this oxygen. And again, this is just the symbol for the oxidizer, whatever oxidizer you happen to be using. So to strengthen the connection to this alcohol, what we're going to do, or to this oxygen, what we're going to do is install a second bond. We're going to make a second bond. We're going to make a double bond. So it's going to be a double bond to the oxygen. And in order to do that, right, in order to make the second bond, what has to happen is this hydrogen needs to leave, and one of these hydrogens needs to leave as well. So we're going to have to pull off 2 hydrogens. Remember, every time we install a double bond, we're pulling off 2 hydrogens. We're reducing the degree of saturation on our molecule. So this leaves us with a single hydrogen here. Right? We have 1 hydrogen left over. And it makes this thing called a carbonyl group. A carbonyl group is a carbon double bonded to an oxygen. Simple enough. That's a carbonyl group. It can be on the end or it can be in the middle. That's how you get a carbonyl group. And then there's a byproduct, right? We took off 2 hydrogens. So the 2 hydrogens are going to, basically they also go through an oxidation process because there's oxidizer available. So typically they'll become H2O. Certain other products are possible too, but typically you'll end up with H2O as a byproduct because the 2 hydrogens came off, and they'll join up with more oxygen. And the oxidizer gets used up during the reaction, but we usually don't really write that in. So there's these 2 products that are possible. They're called aldehydes and ketones. The difference is where the oxygen was and where the double bond ends up. So if it's a primary alcohol, meaning the alcohol was on the end, you're taking 1 hydrogen off of here, but you leave behind a hydrogen, right? Those are going to leave. Bye-bye hydrogens. But you still have 1 hydrogen left on your carbon. So that's called an aldehyde. Aldehydes are always on the end. We call that terminal. They're on the end. But if it's a secondary alcohol, and you oxidize it, you end up with something called a ketone. And the difference there is that when we take away the hydrogens in order to install our double bond, we don't have a hydrogen left over. That carbon is making 4 bonds. That's going to become important later when we're doing reactions with them. So aldehyde is on the end, ketone is in the middle. This is a relatively simple reaction to predict. Here I've just drawn a bunch of alcohols, and all you have to do is take away the hydrogen and make a double bond. Right? Take away the hydrogen, make a double bond. Take away the hydrogen, make a double bond. Same thing will happen over here, hydrogen, double bond, right? This will actually have 2 in the same molecule. Here we have methanol, right? You would take away the hydrogen, take away this hydrogen, and make a double bond. And you end up with what we call formaldehyde, methanol. One thing too that's very, very important is that tertiary alcohols won't oxidize in this way. There's no reaction. This doesn't happen, right? No reaction. Why not? Well, it's because of this, right? We have to pull off another hydrogen in order to install the double bond. We can't make a second bond here. If we made a second bond there, then this carbon would be seeing 5 bonds. We can't lose these carbons. Tertiary alcohols do not oxidize. That's something that's important to point out. So that we get aldehydes, we get ketones. And then you might be thinking, hey, I've got another hydrogen here. What if I oxidize an aldehyde? Well, that's the next step here. So I'm going to pause. What happens when we oxidize an aldehyde? We can oxidize it. We have a hydrogen to pull off, right? So we can oxidize it again. But in this case, it's not like we can triple bond to the oxygen or anything like that. What actually happens is we create this kind of new group where this was the existing oxygen that was there before, and kind of a new oxygen comes in. So the oxidizer basically installed the oxygen there. Let's create something called a carboxylic acid. So this group, the COOH group, which is this group here, that's the COOH group. That's called a carboxyl group. Compare that to carbonyl. So carbonyl is just double bond oxygen. Carboxyl is double bond oxygen and another OH. Properties: this has a very strong hydrogen bond. These ones don't have hydrogen bond capacity because the hydrogen isn't directly attached to the oxygen. But these ones do. There's an oxygen directly attached to a hydrogen. Right? The oxygen directly attached to a hydrogen, so that can hydrogen bond. And it's an extremely strong hydrogen bond because there's another oxygen here. Right? So if we think about like our dipole moment, this oxygen will pull this way, and this oxygen will pull this way, and this oxygen will pull this way. So you're going to get a very, 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 very strong positive charge on this hydrogen. I'm actually going to make this in mole view and show you guys the electron cloud. Here's that same molecule in mole view. 3 carbons and then the carboxyl group. The same molecule, 3 carbons, carboxyl group. Here's the 2 oxygens. You see the 2 oxygens there and there. And look at how blue that hydrogen is. It's just this really strong area of delta positive charge. It is in fact so strong that if this happens with water present, the water can actually rip off that hydrogen. This hydrogen is so positive that when it coordinates to the lone pairs on the water, it will actually just join the water and make what we call hydronium, leaving behind this anion. And that means that this thing has lost a hydrogen. It has given a hydrogen to the water, and that is an acid property. That's why we call them carboxylic acids. is this extremely strong delta positive on this hydrogen. This anion is stabilized by resonance. Right? It's relatively stable because the negative charge can jump between the two oxygens, like we've talked about before. So it makes it even more likely to be an acid. So that's carboxylic acids. They've got these cool properties, and they get created by oxidizing an aldehyde. And we can summarize that in this kind of table. Right? A primary alcohol, here we have propan-1-ol, is going to oxidize to an aldehyde, which is going to oxidize to a carboxylic acid. So this is an aldehyde, and this is a carboxylic acid. I'm just going to write carboxylic acid. A secondary alcohol is going to oxidize to a ketone, but after that it won't oxidize because there's no hydrogen to pull off. There's nothing to, you can't attach more to this. And then a tertiary alcohol just won't oxidize at all. Right? There's no way to install a double bond because you've already got 3 bonds to the carbon there. Sometimes you'll see people actually add the H there. It's very common to put the hydrogen on your aldehyde. So yeah, sometimes you'll see that as well. But that's still just an aldehyde. All right, back to carboxylic acids for a second. Carboxylic acids, many common acids are carboxylic, especially like organic kind of acids. So some examples: citric acid, it's actually got 3 carboxylic groups on it, 3 carboxyl groups on it, and an alcohol group. It's kind of cool. Ascorbic acid, vitamin C, technically not carboxylic, but there's a lot of like resonance stuff going on here, so it kind of acts like a carboxylic acid. Acetic acid, which is the stuff that's in vinegar, clearly carboxylic acid. Lactic acid is kind of got that cool carboxyl group here and then an alcohol group here. Palmitic acid, docosahexaenoic acid, lauric acid, different fatty acids. So that's the carboxyl group on those molecules. Our next section is talking about naming these things. So naming these works a lot like alcohols. Remember, alcohols get this "al" ending. Aldehydes get an "al" ending. They're "al" ending. So this is butanal. Butanal. This would be propene, because there's a double bond there. Propenal. Usually aldehydes don't actually need a number because we know they're on the end. Kind of like how alcohols, if it's in a ring, you don't need to put number 1 because wherever the alcohol is, that's number 1. Same thing with aldehydes. Aldehydes usually don't need a number. They're always on the end. So it's called terminal. Now ketones, same thing like alcohols, right? Alcohols "al", aldehydes "al", ketones get "one", and very much alcohol-like naming. So here this is called butanone. This is heptan-3-one. You might be wondering why I didn't put a number, why I didn't say this is butan-2-one. Well, this is the only way to make butanone, right? If this ketone was on this, that would still be butan-2-one, and if it was on the end, it would become butanal. If we go back over to this, we can name these. Using, I need a red marker. Here we go. We can name these things. This is 1, 2, 3. This is propanal. That's propanal. And this one here, this ketone, is going to be, because it's a ketone, it's propanone. Propanone. We don't need a number. It's not 2-propanone. It's just propanone because that's the only possible propyl ketone. It's the only possible propane ketone. Remember again that the AN is about single bonds. The AN, because you can have enals and enones and stuff too. And then the carboxylic acids. Carboxylic acids also just have a name to end, a suffix. Suffix is oic acid. So, if you have butane, which is for carbons with single bonds, and it's a carboxyl group, you get butanoic acid. Right? So carboxylic acids are always terminal, and the thing about carboxylic acids is they have the highest priority. They are number one in priority groups. So they're always going to be carbon number one. That acid carbon is going to be carbon number one. So they never get a number. So this is called 6-bromo because bromo's on 6. Heptanoic acid because that carbon is carbon number 1. 1, 2, 3, 4, 5, 6, 7. So we can also name this guy here. That's a carbon. 1, 2, 3, 2, 3. So this is propan, and for single bonds, oic acid, and that's actually got a space in it. So it's one of our molecules that actually does involve a space. There's a space between the two. So that's how you name those things. We're gonna do one more thing here with naming, which is now we have this idea we can have these conflicts. And this is the kind of conflict that we could get. Let's look at this molecule here. Right? They have different endings. We have ane, all, one, al, and all we've learned so far is endings. Right? These have all just been from endings. Right? Propanal, propanoic acid, propanone. So what happens if we get a molecule like this? Well, let's talk about priority first. In terms of priority, ketones in the middle aren't as important. Aldehydes are on the end, so they're more important than ketones. And carboxylic acids have that acid hydrogen, and they're just a more interesting group. So yeah, they're the highest priority out of everything. Carboxylic acids have the highest priority. So what happens if we get a molecule like this? This is obviously an al, because aldehydes have a higher priority than alcohols. So we're going to name it with the aldehyde as the priority. So this is going to be number 1, right? 2, 3, 4, 5, 6, 7. So let's think about how we're going to name it. It's going to end in al because it's an aldehyde. It's got 7 carbons. It's a hept. Hept, it's all single bonds for the carbons, so it's a heptan al. It's some kind of heptanal. Doesn't need a number because we know aldehydes are always on the end. But how do we name this guy, right? This OH group. We can't go, I guess theoretically, this is number 5. You could kind of go 5, all, al, but that seems odd. So there's a different, process here, and that's naming the alcohol as a side chain instead of the main chain. So if we name the alcohol as a substituent, we call it hydroxy. So this is 5-hydroxy heptanal. 5-hydroxy heptanal. So that 5-hydroxy refers to the OH group. The OH group over here on 5. That's 5-hydroxy. 5-hydroxy. And then we have other ones. So if it's an alcohol, it's hydroxy. It's hydroxy. I think for obvious reasons, OH, right? Hydrogen, oxygen, hydroxy, OH. Up here, OH. If it's a ketone, you've just kind of got an oxygen hanging off your molecule. Right? Yeah, let's just draw a quick ketone here. For a ketone, you've just kind of got a double bonded oxygen hanging off of it. Right? The ketone, just double bond oxygen hanging off of it. So that's called oxo something. For aldehyde is kind of a weird one. It's formal. Formyl. Which is based on formaldehyde. And you can use that as a side chain. So I don't know, we'll just do another one here. Let's put an OH here, and we'll we'll terminate it with carboxylic acid. How about that? Let's do that. We'll make a carboxylic acid at the end, like that. So if we wanted to name a molecule, oh, I want an O there, and then an H. If we want to name a molecule like that, it's clearly a carboxylic acid. And it's 1. That's number 1 automatically because it's the carboxylic acid. It has to be number 1. 1, 2, 3, 4, 5, 6, 7 again. So it's a heptan, and for the ane, heptanoic acid. It's some kind of heptanoic acid. And then we're looking at this is 1, 2, 3, 4. It's a 4-oxo. 4-oxo. 5, 6, and the 6, because of alphabetical order, 6-hydroxy 4-oxo heptanoic acid. Heptanoic acid. Right. So we have these different names for them if they are lower priority, if we're going to name them as a side chain. Now those names can be found in your priority list. In this priority list picture, you can see, for example, alcohol has this all ending, but if it's a prefix, it's hydroxy. Ketone has an -one ending, but if it's a prefix, it's oxo. Aldehyde has an -al ending. If it's a prefix, it's formal, and various other ones as well. So that is how we name these things. And that's doing some priority work and some naming. The last piece here that we're talking about is reactions. So reactions, we made them by oxidizing, right? Here's our oxidation kind of chart. So the only reaction I'm going to talk about is going back. So you can do this with hydrogenation, same kind of reaction conditions as hydrogenating a double bond, hydrogenating an alkene. Because it is a double bond, and we're just installing hydrogens on each side of the bond, right? If you think about it here, we added this hydrogen to it. We also must have added another hydrogen down here. We've added hydrogen. The H2 gets added across the two sides. So hydrogenation is technically an addition reaction, which gets confusing because it's called a reduction based on electrochemical principles. So it's kind of weird. The opposite of oxidation is reduction. Take ethanol and do the same thing. You install a hydrogen here, and you'll install another hydrogen here. Sorry, you're not installing a hydrogen there. You're installing a hydrogen here, right? You're going to install a hydrogen there, because that's that OH. And you're going to install another hydrogen on here. There we go. And that would make ethanol. That's where the two hydrogens go. H. So that's a reduction reaction. There is a shortcut here. Much like this just has an O, you can do a shortcut where you just write an R, right? Oxidation and reduction. Right? Going back the other way is reduction. Going back the other way is reduction. In terms of kind of controlling it, like if you want to go from a primary alcohol to an aldehyde and stop there, there are certain reagents that you have to choose that will only oxidize it one step instead of two. Same thing if you're at a carboxylic acid and you want to go back to the aldehyde and not all the way down to alcohol. There's specific reducing agents that you need to choose that will stop it at the aldehyde and not go down to the oxygen. That's a more complicated thing, maybe like a second-year organic chemistry in university, something like that. But yeah, it's just a bunch of stuff to memorize. We're only interested in the basics, so we're not going to really talk about that. I think that's actually it. Properties is the last thing we want to talk about. So properties, they're aldehydes and ketones are polar because of that oxygen, the influence of the oxygen, and because it's trigonal planar as a geometry. But they won't make hydrogen bonds, right? Because the oxygen has to be attached directly to a hydrogen in order to make hydrogen bonds. Ketones are typically weaker because they're because the oxygens are more in the middle instead of at the end. Aldehydes are stronger because they're on the end, but they have very similar boiling and melting points and stuff. Just typically aldehydes have a higher boiling point and melting point than ketones, with certain exceptions. Alcohols still win out, so alcohols still have a higher boiling or melting point than ketones and aldehydes, but they're definitely better than the alkanes and alkenes and alkynes because of that polarity, because of those dipole forces. Alcohols, of course, can hydrogen bond. And carboxylic acids are the strongest of all. So these are the kind of general rules. I've just done some 3-carbon ones just to show it off. You know, the just basic non-polar stuff is the lowest melting point and boiling point. Then you'd probably have a ketone and then the aldehyde, because the aldehyde is terminal. But sometimes it doesn't work that way. So for example, if you actually look it up, the boiling points, the acetone boiling point is actually higher than the propanol boiling point. So there's some interesting little kind of things that can change it, but they're pretty close. They're very close. It's like 50 degrees versus 56 degrees. Very, very close. Then you got your secondary alcohols. Then you got your primary alcohols, and then you've got your carboxylic acids in terms of boiling point. And I guess there's kind of a middle one here, which would be a tertiary alcohol, but there's no propyl tertiary alcohol that would sit, there. Yeah, so I believe that's it. Let's see, is that everything? That is everything. All right, so let's review what we talked about. We talked about oxidation of alcohols and making the carbonyl group, then the fact that aldehydes can get oxidized again to make a carboxyl group. We talked about naming aldehydes, which get an al ending, ketones, which get an one ending, and carboxylic acids, which get an oic acid ending. Then we talked about what happens when you have multiple functional groups and there's a priority conflict. That's where you have to start talking about those prefix namings, where this is now hydroxy instead of ending in all, and then some reactions of aldehydes, ketones, and carboxylic acids, specifically just reduction of them for now. We will talk about some more reactions of carboxylic acids in Monday's lesson, but for now that's it. So that was a short one, less than 30 minutes, but we're going to get lots and lots of practice for this stuff in class. So yeah, I'll see you in class.